Okay, so what is the reason that we care about the reactivities of these different metals, right? Like, what's the application here? Well, this is actually all of these differences in reactivities is kind of the entire reason that a battery works, right? So, a lot of the electronics you use every day, uh, you owe to this fact that some metals like to reduce more than other metals, right? So, what I've set up here is actually, it might not look like it to you, but this is a battery. Okay, I'm going to show you, or it's almost a battery anyway. Okay, this is going to kind of bring together a lot of concepts that we've talked about so far. So first, let me just walk you through everything that I have here in front of me. Okay, so in this one, if you can read that, I have solid zinc. That's this piece of solid zinc. That's just a piece of metal, zinc. Okay, in a zinc sulfate solution. So that's an ionic solution, right? So when I have zinc sulfate dissolved in there, right? An ionic compound dissolved in solution. What kind of solution would we call that? Well, it's ionic, so it will be an electrolyte, right? It will conduct electricity. It will allow electrons to flow through it. Now we have on this one, similarly, we have copper. So that's solid copper, just copper metal, right? A bunch of copper atoms, okay, in a solution of copper sulfate. Copper sulfate is blue. Copper ions, when they dissolve in solution, they turn blue. Okay, so it looks delicious. It's like forbidden Kool-Aid, though. You can't drink it. Would not taste good. Would not be good for you. Okay. However, we have again we have solid zinc atoms in a bunch of zinc ions and sulfate ions. We have solid copper atoms in a bunch of copper ions. Okay. Now what have I done here? What have I rigged together? Well, I've connected them with a wire, right? I've connected them with a wire. And I could have just connected them, but I chose to connect them through this. It's called a voltmeter. Basically, what a voltmeter will tell me is if electricity is flowing or not, right? So if electricity is flowing, you should see this needle here. It might be kind of hard to see on the video, right? I can bring it closer. But if electricity is flowing, you'll see that needle move. So you can tell right now there's not electricity flowing, right? So maybe saying, what's the point of this? Just wait, we'll get there, okay? And then on the other end, I've kind of connected them. So through the voltmeter, if electricity is flowing, it'll have to go through the voltmeter, make the needle move, and then into this red wire, and finally into the copper. So they're kind of connected right now. The zinc and the copper are connected, okay? So since zinc and copper are one is better at reducing than the other, right? In fact, I've even drawn, if you look on your table on page 4 on your activity series, right? Copper is above. So if you remember the stuff at the top, right? It is better at reducing, or it wants to reduce. So this reaction really wants to happen, right? Uh, wants better at doing this, okay? Which is, of course, reducing. It's gaining electrons. Where the stuff down here is, it would rather do this. It would rather do this. It's better at doing this, oxidizing. So when they're connected by a wire that could carry electrons, right? Oops, you can't see that. There we go. Better at doing this. So this at the top here, that's better at going that way, whereas the other one's better at doing this. So we have basically a whole bunch of copper ions in a copper solution. Now, what is it better at doing? Well, copper in general is better at reducing. So it's better at taking electrons, gaining them, right? What about this guy, zinc? Well, zinc is better at oxidizing, doing this, okay? So zinc is better at losing electrons. It's okay with losing them. If copper is better at taking them, zinc is better at losing them. They are now kind of, I think of it, they're connected by something that can carry electrons, right? A wire, a conducting wire that can carry electrons. So they kind of are in like a tug of war now for electrons. And who wins? Well, copper's better at taking electrons. So the copper electrode, we call this, okay, this is an electrode. The copper electrode will take it from the zinc electrode, okay? But the issue is, copper is good at taking electrons, right? But think back to Science 9. What do we know about like charges, the same charges? Well, they repel each other. So as copper starts to take electrons from zinc, pretty soon copper is going to get really negative with all those extra electrons, right? And it's going to be over. There's no completion for the circuit, right? As we know from grade 9, electrons need a circuit to be completed. So notice, Yep, they're connected. This is even a conducting solution, so that's good. The water can even carry some current. So can, well, the solution, it's not water. This solution can carry some current. However, there's a break in our circuit, right? It's like we've cut the wire. How can I fix this? Well, I've made a third kind of solution here, just sodium chloride, right? We've seen that a lot this section, but sodium chloride is a electrolyte. It also conducts electricity. So what if I use it to complete the circuit? Okay, so as I do this, I'm going to try and prop that up. It's kind of far away, but I'll show you. Okay, hopefully you can kind of see that. So the needle right now is there. Okay, it's right on the 0. I'm going to take this uh, sodium chloride soaked, it's just a piece of filter paper soaked in an electrolyte. So it's soaked in something that will conduct electricity. And I'll move out of the way and I want you to watch what happens. Do you see that? Look at the needle. Wow. Okay, look at the needle. So, can't figure out my fingers. That's where they want to be. Look at that. So, is it a bunch? No, but this is a pretty simple setup, right? This isn't something super fancy. So I can even, here, how about I move this closer to you and I'll play with it a bit. So notice that it's conducting a little bit of electricity. If I remove the salt bridge, I break the circuit, okay, and nothing. Same if I remove one of the electrodes. So what if I take the zinc out, right? Now I've broken the circuit. They're not connected. So this is called a voltaic cell. This is essentially how a battery works. A battery is actually a voltaic cell, right? Or it can be a combination of many voltaic cells. Okay, so we're going to go a little bit more into the definition stuff, but I wanted you to see one, right? It's pretty cool. Pretty cool that you can just build this on your own. In fact, they've actually found evidence of simple voltaic cells in ancient Egyptian like pyramids, right? Ancient Egyptian civilization. So the knowledge on how to make these has actually been around for a long time, right? So just a quick note in case you're not sure what's happening here. What is happening? Electricity is being produced. All electricity is the flow of electrons. So as they get pulled over to copper, right, electricity is now flowing. I could hook a light bulb up to this and it would light up. As a matter of fact, remember this guy, our conductivity meter? Well, what happens now if I hook the end that's the copper, right? I hook that up there, and then I take the end that's the hooked up to the zinc. Look at that. Wow, 2 different electrodes. So they are completing the circuit. They are allowing electricity to flow and they are lighting up that bulb, right? Without me even dipping it in there. Okay, so this is pretty much, it might not look like it, but this is essentially how the battery in your flashlight works. Same idea. Okay, we've gotten a little better at making batteries, and yes, they're a little bit fancier now, but this general principle is the exact same thing. Something likes taking electrons more from something else. So if you connect them with a wire, they'll kind of have a tug of war of electrons. And then if you complete the circuit in an electrolyte, so that current can be carried through, you got electricity flowing. Okay, so back to our notes really quick. We're on page 8 now. Okay, this is our kind of our last topic. We're just now going to look at the applications of these ideas of reduction and oxidation, something that you kind of use every day, even if you don't realize it. Okay, so like I was just showing you, I was showing you a voltaic cell. Okay, so here's the key. A voltaic cell uses spontaneous redox reactions. What does that word spontaneous mean again? It means, remember, it kind of wants to happen. Did I have to put in any extra energy to make that happen? No, right? I didn't have to force it. I just connected them. As long as I completed the circuit, hey, boom, electrons were flowing from the zinc to the copper. Okay, so this is actually the exact same one I set up just because I felt like it, except the difference is my salt bridge just contained sodium chloride, not potassium sulfate. But really, the salt bridge doesn't matter. All that matters is that it conducts electricity. What you make it out of doesn't matter. So I just want to touch quickly on the main kind of difference between a voltaic cell. We're going to write it here, and then when we look at the other kind of cell, we'll see what the difference is. But in a voltaic cell, we're taking this kind of chemical potential energy, this difference between the two, and we're turning it into, what kind of energy are we making here? We're making electrical energy, right? Those electrons moving, that's electricity. That's all electricity is. So here we are taking chemical, in a voltaic cell, we take chemical energy, and we use it to make electrical energy, right? Again, a battery, right? A battery you would put in your, electrical Energy, chemical energy to electrical energy. That is what a voltaic cell does, right? A battery is full of chemicals. You put it in your flashlight, and your flashlight, electricity flows, and then that electrical energy gets turned into light energy, technically, right, in a flashlight. But the point is, the chemical energy in the battery gets turned into electrical energy, and then you use the electrical energy for whatever else. Okay, so we use spontaneous reactions here. That's another important thing. Voltaic cells are spontaneous. So what did we do? We just connected two things. One was a better oxidizing agent, which means it is better at reducing, right? So it pulls electrons away from the other through the wire. Okay, that's what we set up on camera there a second ago. So we have zinc connected to copper through a wire, and if we want to measure it, we can put a voltmeter in there. But since they're connected, copper is going to yank on zinc's electrons. It's going to steal them away. Okay, so because they're connected by a wire, I think of it as a tug of war, right? They start a tug of war for electrons. Copper wins because it's a stronger oxidizing agent. It's better at reducing, okay? So I think of it as it's above zinc on the activity series, okay? When I'm looking at these, I actually kind of think of this as like uh, a, a criminal organization or something like the mafia, right? These guys at the top, they're good at stealing from other people. They're kind of the top head honchos. So if they want electrons, guess what? They just take them, right? If you connect gold to anything below gold, it'll just take its electrons. So when we're looking at a voltaic cell, since we're just connecting two things, which one's going to get the electrons? Hey, whichever one's on top, because it's better at reducing, right? So we connect them, they start a tug of war, and the strong ones win. The ones on the top are going to take the electrons from anything below them, right? So if we connect copper and zinc, right, we go to our reactivity series. We find copper and we find zinc, and in these, it doesn't matter since both ions and metals are present, we're just saying, hey, who's higher? They're better at reducing, they're going to take electrons. So in this case, the copper ions are taking electrons from the zinc solid, but really what we're thinking about is just, copper's above zinc, so copper wins the electrons, okay? Because we have both ions and atoms present, so in this case, the ions are taking electrons from the zinc, okay? Now, since electricity is nothing more than the flow of electrons, and electrons are flowing, we're now making electricity, okay? That's actually where the word electricity comes from, because electrons are moving. All right, so as electrons leave the zinc electrodes, zinc becomes zinc 2 plus, right? Hey, what do we call that? Zinc becoming zinc 2 plus, going from 0 to 2 plus. That's getting less negative. Hey, that thing's losing electrons. Leo, this thing is oxidizing, okay? Now, the thing is, remember, we always say zinc S, and then we would say zinc 2 plus aqueous. What does the aqueous part mean again? It means, remember, think of an aqueous solution. It means it's dissolved in water. So what is really happening is that the zinc is dissolving off of here, okay? The zinc, as the electrons leave, you're left with zinc 2 plus, and it comes out into the water, okay? And so the zinc electrode will shrink. It actually literally will shrink. It will dissolve. The zinc electrode shrinks as the cell runs. This is actually kind of a popular way to make really sharp knives and things. You can set them up, hook them up in a voltaic cell, and as it dissolves, you can get really, really sharp edges if you want, okay? So as electrons arrive at the copper, now those copper ions that are in here, they're going to see those negative electrons arriving, okay? So we're going to get a whole bunch of electrons arriving here at the copper, and they're going to say, oh, I want one of those, right? Because they're positive. They would like to get reduced. We also know they're very good at reducing, right? And a positive charge will be attracted to a negative charge. So a copper goes and picks it up, and it gets stuck as solid copper. And it starts to do this a whole bunch, and it actually starts to build up on the edge, right? So this guy's dissolving. Zinc ions are kind of coming out. It's getting dissolved, right? Zinc is coming out of it as ions. It's getting dissolved out, okay? But copper is building up on this one. So this one is actually going to grow. The copper is actually going to grow. So as electrons arrive at the copper ions in the solution accept them. They get reduced, right? They gain electrons and become solid copper. So the copper electrode grows as the cell runs. As the cell runs just means as electricity is being produced, okay? And so the salt bridge just allows the electric circuit to be completed, okay? And it allows ions to basically move where they need to go to keep everything from being too positive. Because after a while, this is going to start to lose a bunch of its ions, right? And this side won't be that positive anymore, which means electrons won't really want to go over there that badly, right? Remember, opposites attract. Same opposite's going to happen over here, but for the same reason, right? So now the positives are going to be leaving. This is going to be getting more and more, losing more and more electrons, and eventually they're not going to want to leave over here that bad, and you're going to start to lose the flow of electricity. Hey, what happens to batteries after a really long time? Well, they die, right? That's what's happening. That's all that's happening, okay? The charge is no longer different enough. There's no longer enough pull to go over there. How can we make it last longer? With our salt bridge, okay? So that just lets an electrolyte kind of pass to where it needs to go. Okay, so in this one, we have a salt bridge that is made of potassium sulfate, I believe it says, K2SO4. Yes, K2SO4. So what's K2SO4? It's an ionic compound made up of K plus and sulfate, SO4 2 minus. That's another one from your table of polyatomic ions, right? So as the copper 2 plus is getting turned into copper, right, this solution is getting less and less positive, right? So as these copper 2 pluses are going, right, and picking up an electron and becoming just copper, it's getting less positive or more negative, okay? So what will happen? Well, to keep it from getting too negative so that electrons stop flowing, this potassium will kind of flow down through the salt bridge, and hey, I'll keep things a little bit positive for as long as I can, right? All batteries die eventually, but it'll do as much as it can. Then same thing over here. As all of this zinc, solid zinc, is becoming zinc 2 plus, right? This solution is getting more and more positive, and pretty soon it's going to be so positive that the negative electrons aren't going to want to leave anymore. So the sulfate comes through the salt bridge. That's why it's called a bridge. It kind of connects 2 points, right? The sulfate and the salt bridge will come over here, and hey, I'll make it a little more negative over here so that the electrons still do want to flow out. So the salt bridge just allows A, the circuit to be completed, and B, keeps it going longer. Okay, so again, this is exactly how a battery works, right? So this is like your, let's say, AA battery. You've got the positive side, the negative side. Okay, electrons are going to flow from, in this case, this would be zinc, right? And it would go through the light bulb to, in this case, copper. Copper is stealing the electrons from zinc. We're going to now look at those words cathode, anode, and we know the word electrolyte, right? If you connect them with an electrolyte, which they are kind of connected with an electrolyte. Here's an electrolyte, here's an electrolyte. How are they connected? By the salt bridge, right? Bridges connect things. Okay, we'll get to those words in a second here. Well, as in right now. Okay, so here we have anions, right? Remember, how do you remember what an anion is? The N is for negative, right? Anions are negative ions, okay? And they would be attracted to the anode. So the important thing, oxidation, remember Leo, so oxidation, losing electrons, okay, occurs at the anode. So we say anox. Anox is the thing that helps us remember where oxidation is happening, okay, or what we call the thing that is being oxidized. Because to be honest, it's easier to figure out what is being oxidized than it is. That's how you figure out what the anode is, okay? Now, reduction occurs at the cathode. So cations, remember the T looks like a plus. If you write out, it looks like a plus sign. So cations are positive ions. They are attracted to the cathode. That makes sense. Cations go to the cathode, anions go to the anode. Okay, now here's the thing. Reduction occurs at the cathode. The way we remember that is red cat, right? So since reduction is occurring there, again, that means it's gaining electrons. Okay, I'm going to add something to this. Not just red cat. I'm going to add, red fat cat. And that's not just to be mean to this cat. It helps us remember something. So remember that rhymes, right? Red fat cat. Why fat? Because remember, well, first of all, let's look at this. What's our anode? What's our cathode? Remember, anox, red cat. So if it's being oxidized, if it's losing electrons, it's anox, so it's the anode. Okay, so this thing is losing electrons. Zinc is losing electrons. So oxidation is happening here, right? Oxidation is here, happening to zinc. So what kind of thing is this? This is our anode, okay? And it's going to shrink, right? It's going to shrink. Over here, over time, right? This is our it is being reduced. It is gaining electrons, right? It's gaining electrons. So this is being reduced, red cat. So it's being reduced. Copper is being reduced, and it is red cat, red fat cat, right? So it's the cathode. Why did I add in the fat? What's going to happen to it over time? Remember, these copper ions are going to go pick up electrons, get reduced into just plain old solid copper, and they're going to start sticking on the edges of that cathode, okay? So to do a bit of review of terms here, these are both called electrodes, and then there are basically two types of electrodes. There's anodes, where anions are attracted to, right? Notice how the sulfate anions are attracted to the anode, and there's the cathode. Okay, that's the other type of electrode. Notice how the cations, the K plus, is attracted to it, and same with these cations, they're attracted to it, right? Here we have a cation, and what's it want to do? It wants to get away from the anode. It is not attracted to the anode. Okay, so looking back at our battery, we have our positive and our negative terminal. We call the anode and the cathode, right? So to me, how do I remember this? I always go with like the criminal organization, right? The mafia or whatever. I say whoever's on top is going to take whoever's below its electrons. Once you know who's taking electrons, it's actually pretty easy to figure out everything else, right? So a question might ask you, where is oxidation happening? What's the anode, right? Really, all those are saying is variations of who is taking electrons, right? Whoever's taking electrons, they're being reduced. So red cat, that's the cathode, right? Whoever is having electrons taken from them, well, they're being oxidized. Anox, that's the anode. Okay, so when we're looking at our table, we're going to be given two things that are connected, right? This is our activity series on page 4. We're going to be given two things that are connected, whichever one's on top, right? So we're given blah, blah, turns to blah, blah, right? And then blah, blah turns to blah, blah. Well, whichever one's on top of the two things that are connected will always be whichever one's on top is always going to take the electrons, right? So it takes E minus, it's higher. So if it's taking E minus, it's gaining electrons, grr. So it's being reduced, and red cat, red fat cat. Okay, so this is the cathode. And the question might ask, hey, which one's going to get bigger? Which one's going to shrink? Red fat cat, red fat cat. So it grows over time. Okay. Then down here we have the blah, blah to blah, blah. All that matters is it's lower, right? So it's worse at reducing, so it gets oxidized, okay? So this loses. It gets its electrons taken by this other guy who's higher up in the criminal organization, higher in the mafia, okay? Loses E minus. So when you lose electrons, Leo, oxidation, okay? So it's oxidized. Anox. So anode, okay? And then if you can remember always do the red fat cat first, because if you can remember that one, then you can remember, well, if that one grows, this one's shrinking. Shrinks over time. It dissolves over time. It's literally being dissolved into solution, okay? We won't have time to do it, but I've run voltaic cells for the entire chemistry unit before, and by the end, the anode was almost gone, right? And the cathode was getting really thick. It was getting quite chunky. Okay, so what's a typical question for this kind of stuff look like? Well, I'm glad you asked. Okay, let's take a look. So this is actually a typical way of representing a electrochemical cell. Okay, and all this means is we got silver, one of them silver solution. Silver ions are in the solution. Then we've got zinc ions in a zinc solution, and a zinc solid is sitting in it. Okay, so again, we have all the ions, all the atoms, okay, present in both. We just got to figure out, hey, which ones are better at taking electrons? Salt bridge just keeps it going and also completes the circuit. So silver is placed in a silver nitrate solution, and zinc is placed in a zinc nitrate solution, and a sodium nitrate salt bridge joins the two beakers. So we've got silver and zinc. We got to compare those two things. So it asks us to label the voltaic cell diagram using the above components. So let's just go ahead. I'm going to pick one and make one side and make one the other. So let's go ahead and make this one silver. So that piece of metal is going to be made of silver, Ag solid, right? Okay, which makes this one, if this is the silver side, we'll make this side zinc, solid zinc. So it's like mine that I made for you, except instead of copper, it's silver, okay? So if it's placed in silver nitrate solution, okay, so silver is placed in a silver nitrate solution, that means floating around in here are silver ions and nitrate ions, right? So NO3 minus. A whole bunch of them, billions of them are floating around in solution. I'm not going to draw all of them. That means over here where it's placed in a zinc nitrate solution, what's floating around in here? Well, the two ions that make up zinc nitrate. So zinc 2 plus, okay, and nitrate, NO3 minus. Okay, the salt bridge contains sodium nitrate. So a sodium nitrate salt bridge joins the two beakers. So in here we have our salt, right? We have our sodium nitrate, NaNO3. Okay, is it table salt? No, but salt is a more general term than we use it in our day-to-day life. Okay, now it asks, that's done. Okay, good, we labeled it. Now write out the oxidation and reduction half reactions and make sure to label them. So we got to think about who's being oxidized, who's being reduced. Okay, so first things first. What I mean is, okay, first things first, when you're given something like this, figure out where electrons are going to go, and everything else falls into place after that. Okay, so I want you to pull out, go to page 4 of your data booklet, take a look at your activity series, okay, and think about like the mafia, like a criminal organization, right? And say, okay, the guys on top are going to steal from the people below, right? If they want their electrons, they're just going to take them if they're connected. So here we have silver connected to zinc. Who is going to take electrons from who? I'll give you a sec. You pause it and take the time to find it, or if you've already found it, silver is definitely above zinc. So these silver ions are going to take electrons from the zinc. Okay, so which way are electrons going to flow? Kind of, I always think step one, just figure out what the electrons are going to do and then draw that in. So here go the electrons. Okay, E minus, they're going to go through the voltmeter, make the needle move just like we saw. Okay, and then they're going to go into the silver, which will then, these ions will go pick it up. Okay, but now that we figured out which way electrons are going, life gets a whole bunch easier because, hey, what's going to be oxidized now, right? Now we can actually say, well, oxidizing is losing electrons, right? Oxidizing is losing electrons. So it's pretty clear now that we know who's going to take them, who's losing them, right? It looks like zinc is losing its electrons. So let's just write that in. Zinc is being oxidized, right? It's losing its electrons. Leo. Okay. See them leaving? Okay. Hey, zinc, it's being oxidized. Oxidized. Anox. Anox. So what is zinc? Zinc is the anode. Okay, over here now, silver is taking those electrons. It's getting more electrons. It is gaining electrons. Gaining electrons. Right? Gaining electrons. So what is it doing? This is being reduced. Okay, reduction is happening here. Red, fat cat. Red, fat cat. So this is the cathode. Okay. What's the fat part mean? It means it's going to grow over time. Okay. So it asks us to write out the oxidation and half reaction. See how much easier it is now to just, now we know what's going to be oxidized, what's going to be reduced. Let's go ahead and write out our oxidation half reaction. So zinc, what is the oxidation? Zinc is going to lose electrons, right? So it's going to lose electrons. So what is happening to zinc here? As these electrons leave, what change is happening? Well, zinc is getting dissolved and it's becoming more zinc 2 pluses, right? Zinc atoms are going to dissolve into zinc 2 plus as electrons leave. So zinc, solid zinc, right, is going to become aqueous zinc 2 plus. How did it do that? How did it go from 0 zinc to zinc 2 plus? Well, it must have lost 2 electrons. 2 electrons broke off, right? They used to be together and now they're not. We can also think of it as now 2 plus over here, 2 minus over here. Good, that matches with the 0 we started with for charge. What's the reduction half reaction? What's happening over here? Well, as the electrons arrive here, as it's getting reduced, as the electrons arrive here, well, what are these silver ions that are in solution going to want to do? They're going to want to go pick those electrons up, and then they're going to harden into solid silver. So silver is going to start to build up on the edge here. Hey, that's why the red fat cat, right? So then we're going to have, what's it going to do? Silver ions, like we just said, aqueous silver ions that are dissolved in water are going to pick up an electron. They're going to meet an electron, and then afterwards, they're going to be stuck together, right? The electron is going to be part of the silver now. Okay, there we go. So which one's reduction, which one's oxidation? Well, in this one, the electrons are breaking off. It's losing them, right? This is oxidation. Losing them, Leo. In this one, it's picking up the electron so that afterwards they're together. So it's gaining that electron. Reduction. Okay, there's our half reactions. Hey, look, we already did see, label the anode and the cathode. See what I mean? Once you put the electron flow into place, it's really easy to tell. Everything else kind of bang, bang, bang falls out. Oxidation anode, we already did that. Good. Show the direction of electron flow. That shouldn't be step D. If you ask me, that should be step A. Anytime you do one of these, just say, hey, which way are electrons going to flow? Do that, and everything else falls into place. Which metal will increase in mass? See, I didn't lie to you. Once you figure out the electron flow, everything else falls into place if you do it in order, right? Red, not just cat, red fat cat. So why is it called the fat cat? Because it's going to grow when those positive ions go pick up an electron that just got there from over here at the anode, right? The anode just lost its electron. So it's dissolving, it's slowly shrinking. If you remember that that one grows, you can remember that this one shrinks over time. Okay, so the longer electricity is produced, the bigger this silver electrode is going to get, the cathode, and the smaller this zinc anode is going to get over time. Okay, last thing for this week's topic is electrolytic cells. If you get voltaic cells, you can think of an electrolytic cell as basically a backwards voltaic cell, in a sense. Okay, that's a bit of an oversimplification, but hey, remember, what kind of energy did voltaic cells start with, and what did they turn it into? Right? They started with chemical energy and turned it into electrical energy. What do you think electrolytic cells? They start with electrical energy, okay, and they turn it into chemical energy. Why would you ever want this? Well, do you have something that starts out with chemical energy in the morning and throughout the day turns it into electrical energy? And at the end of the day, it's all out of chemical energy to turn into electrical energy, so it can't be used anymore. So you have to get some electrical energy. You have to plug it into electrical energy so that you can build up more chemical energy again. Maybe you're watching it right now. Maybe you're watching this video right now on something that does that. A rechargeable phone, right? So any rechargeable battery consists of a voltaic cell and then kind of an electrolytic cell, right? It takes the voltaic cell is the battery part that allows you to get electrical energy all day through your phone, right? Using it, but then over time that chemical energy runs out because you're using your phone all day, right? And at the end of the night, when it's time to plug it in, now you're going to take the electrical energy from your house, turn it back into chemical energy that can then be used the next day, all day, for using your phone again with electrical energy, right? So that is what an electrolytic cell basically, it's a rechargeable battery in its simplest sense, okay? But the thing is, it's non-spontaneous. So we kind of have to reverse what was happening before, okay? So all non-spontaneous means is it won't occur on its own. We have to add energy, okay? What kind of energy do you think we're gonna add based on what we just talked about? Electrical, right? So electrical energy is used to make redox reactions occur that normally wouldn't, okay? That normally wouldn't want to happen. In other words, we're going to force the things to do the thing that they're actually worse at so that the next day they can naturally just keep doing what they're better at, right? We're kind of going to build it back up. It's like knocking down a sandcastle and then building it back up just so you can knock it back down again, okay? So it makes electrolytic cells kind of like reverse voltaic cell, which use chemical to produce electrical. So we talked about that, okay? The idea though, the general idea is the same. So the idea is the same. Nothing actually changes in terms of the cathode and the anode. The anode is still going to shrink and right? The anode is still going to be where oxidation happens. The cathode is still going to grow, red fat cat, and it's still where reduction happens. The only difference is that where on a voltaic cell, you would figure out who's on top of your of your activity series, right? Who's the boss in the mafia. Now we're going to force the other one to take the electron. So a good example is electroplating, right? So like you can plate gold and silver onto cheap metal. So if you have jewelry that looks really nice, it might even have real gold on it, but it didn't cost you that much, right? It was actually pretty cheap. Good chance it was electroplated. Okay, so what that means is, this is the example here. So we have gold, and then these glasses are made of aluminum. Okay, so I'll make it a bit bigger. These glasses are aluminum. Okay, now if you look on your activity series, gold is definitely way above aluminum. In fact, gold's above everything. So gold should be stealing the electrons. And you'd be absolutely right if this were a voltaic cell. But here we're going to use electricity. We're going to use a battery. Okay, we're going to use electricity to force the electrons to go the way they don't actually want to go. We're going to force the gold to give up its electrons to the aluminum. Okay, and what ends up happening now is the gold dissolves. Right, the gold dissolves. The difference in an electrolytic cell, another big difference, is that it's all happening in one big beaker instead of in two separate beakers. Okay, so now these gold ions, these electrons are going over here. These positive gold ions are saying, hey, it's getting pretty negative over there on that, that aluminum that's looking cheap. I'm a gold ion. I want those electrons. Hey, those were my electrons. They stole them from me, right? So this gold is now going to go over to those electrons and pick them up. And then what's it going to do? It's going to stick there, right? The gold is actually going to stick onto the edge. And what you can do is get a very, very thin layer of gold all the way around. So most of your glasses are made of cheap aluminum. Okay, you've now coated your entire cheap aluminum frame of glasses with this just a few layers thick of gold. That's super cheap. You didn't have to use all this gold. You just used a few atoms. Very cheap way to make some aluminum look like solid gold. Okay. So again, yeah, the gold from the anode is dissolved by forcing it to give up its electrons that it normally wouldn't. Okay, so the anode from the gold is oxidized. We forcibly take its electrons without it wanting to give them up. Okay, and then it dissolves. The electrons arriving at the aluminum glasses, frame cathode, reduced, red cat, okay, in solution to that on the surface of the frame cathode. So the only difference, once again, is instead of finding out who's on top, right, or I guess once you find out who's on top, they're actually going to be the ones, we're going to force them to give up their electrons, right? So we have here gold, okay, Au3 plus 3 minus would go to Au, okay, and then somewhere below that we have aluminum 3 plus 3 minus goes to aluminum. Normally, if it was a voltaic cell, we'd connect them and gold would say, hey, give me those electrons, I'm above you, right? But in this case, we are using electrical energy to force the opposite to happen, okay? Now, I know I said rechargeable batteries is a big application. It absolutely is, but I thought this was a cool one to show you as well, right? We force the electrons to go and we do it in the same solution. Okay, so again, what products would you expect to be formed at the anode and cathode? So nothing changes when deciding the anode and cathode. And ox, who's being oxidized, who's losing electrons? Well, the electrons are going this way, right? They're going this way. So who's losing them? Gold. So this is oxidation. This is the anode. Okay, so who's gaining electrons? Well, as they leave the gold, they're going to the aluminum, right? So the gaining electrons over here at the aluminum, gaining electrons. So reduction is happening here, right? And don't forget, red, fat, cat. Red, fat, cat. So yeah, it's getting bigger. That's the fat part. And this is the cathode, okay, cat. So at the cathode, what is being produced? Well, solid gold, right? That's the whole point. As these gold ions get attracted over here to where all the electrons are, they pick up the electrons and they get reduced into solid gold, right? So, okay, so we're not making aluminum 3 plus, that's for sure. So it's not A or D. Let's look at B and C then. At the anode, what is being produced? Well, this solid gold, right? What's happening? It's having its electrons stolen by us. We're forcing it to give up its electrons because this is an electrolytic cell. So we force it to do the opposite of what would usually happen based on our table, right? Do the opposite. It's losing its electrons, so gold is becoming gold 3 plus. It's being oxidized into gold 3 plus. So what product is forming? Well, not solid gold. That's actually what's disappearing, right? What's our answer then? That leaves C. We're making gold ions at the anode, and we're making solid gold at the cathode. That's the whole point, and that's why it's called electroplating. We're using electricity to provide a thin plating of some other metal around something, usually something cheaper, but there's a few applications of it. I'll show you a quick video. It's pretty cool, actually, of doing some electroplating on some bolts. That's how we'll close it out. But well, I'll kind of leave you there, but I'll say for now, okay, you can now do all of the formative work, that entire sheet, that part on electrochemical cells as well, okay? And when you're ready, you can do the summative Google Forms for this week's whole topics. Okay, so in this solution, we have an electrolytic solution, right? You can tell here there's an electrode. Here, there's an electrode that they're actually able to move. And when they touch one to it, they cause it to become the anode. They turn it into the anode. And notice all this pink stuff that's in solution now that's coming from the cathode rushes over. It's really cool to watch. It's actually quite satisfying to look. So now notice they've coated them with a thin, just literally a few atoms thick layer of whatever it is that they're doing. I'm not entirely sure what they're actually coating them with, but this is plating them, I should say, is a better word. This is electroplating. It's really fun to watch. Very satisfying. Cool. Okay, that wraps up our topic. Have a good weekend or whatever time of week it is when you're watching this.